We mentioned spectroscopy is the interaction of light with matter. We took our time to understand the light part of it. We took a very small effort to understand how NMR is exploited for some materials, like in the case of chemicals that we saw. In the case of microwave spectroscopy, we end up looking at bond rotations. For instance, when you have a diatomic molecule, when you have rotations that are possible, you end up looking at the rotational energy levels that are present. You have energy levels that go of this sort with their own multiplicity, and then you have excitations across these energy levels that helps you get the microwave rotational spectrum. And as you go higher in energy, you have the IR spectrum, which ends up looking at bond vibrations. And when you're looking at bond vibrations, you're imagining the harmonic oscillator potential, where the energy is equally spaced as you go farther, and you're looking at excitations across these energy levels. And then when you're looking at the UV visible spectrum, here you're discussing about the electronic transition states of singlet and triplet states that are present. And of course, fluorescence spectroscopy also ends up being a part of this. And the higher energy X-rays would end up probing atomistic details. For instance, X-ray diffraction and neutron diffraction helps you get structures. So the question that we have here, what energy levels does NMR spectroscopy perturb? In order to understand this, without very detailed description, we will try to understand what makes up nuclei. The subatomic particles that are present as per modern day physics are leptons, quarks, and force particles. The most common lepton that we deal with is the electron, which has a charge of -e and a spin of +12. And quarks are of 6 different types. And once again, without going into much detail, you have quarks which are charged -e/3 or +2e/3, each with a spin half. And the most common force particle that we are familiar with is the photon. The light that I referred to you in spectroscopy can be thought about as a flurry of photons that help you excite molecules from one energy level to another energy level. Nuclei is composed of protons and neutrons. Neutrons are composed of 3 quarks, 2 with a charge -e/3 and 1 with a charge +2e/3. And the spins that orient themselves result in a way where these spins pair with each other and you get a spin of half. And a total charge of 0, which we already know since neutrons are not charged. On the other hand, protons are also made of 3 quarks, where you have 2 of 2e/3 charge and 1 of -e/3. Similar to the neutron, you end up having a spin where the 2e/3 spins couples with each other, giving no effective spin, but the -e/3 results in a spin, so you have something like spin of 1/2 and a charge of +e. Since each of the nuclei are composed of protons and neutrons, the effective combination of these spins results in a nuclear spin. For instance, let's take the simplest of nuclei, which is the hydrogen. In this case, you have only one proton that is present, so therefore this comes up with spin half. On the other hand, when you take the heavier isotope of hydrogen, which is going to be composed of one proton and one neutron, you end up getting something like half and half, which is spin 1. On the other hand, when you take the heaviest isotope of hydrogen, which is tritium, you're going to have one proton and 2 neutrons whose spins couple with each other, so you get something like a spin half. Of course, the way of determining spin quantum number for a given atom are more complicated, but I have taken a simpler example to help you understand a nuclear spin is an intrinsic aspect of a given isotope that you end up taking. So therefore, one is able to come up with some simple rules in order to understand how nuclear spin quantum number plays a role. For instance, all these are based upon the mass number. You could either have a mass number that is even or odd. All atoms that have an odd mass number end up having a spin quantum number that is n by 2, basically half integer. On the other hand, the ones that have an even mass number could have atomic number that is either odd or even. One observes the fact that all even nuclei have no spin quantum number associated with them. On the other hand, the ones that have an even mass number and an odd atomic number are associated with integral spin n. Let's take some common examples that we would end up observing or using in NMR spectroscopy. If you take 1H and 3H, which we just saw a moment back, these are spin half nucleus. For that matter, if you are having something like C13, N15, 19F, 31P, these are also very common spin half nuclei. Of course, you could also have other nuclei that have spin quantum number that is 3 by 2, 5 by 2, 7 by 2 and so on. One example is 17O. The even nucleus are also very common, where you have C12, O16, which are the predominant nuclei that are present. These have spin quantum number of 0. And one example for an even odd nucleus is 14N and deuterium, both of which have a spin quantum number of 1. You also have some examples of spin quantum number of 3, but then integral spin quantum number is rarely observed. With this in mind, one is able to understand the spin quantum number I that we will be referring to from here on is associated with the kind of nucleus that we are dealing with, which is characterized by its atomic number and mass number. Any nuclei that has 0 nuclear spin quantum number will not be NMR observable. On the other hand, nuclei that have a non-zero nuclear spin quantum number are observable by NMR spectroscopy. Of all the nuclei, the most commonly observed nuclei are proton and the carbon 13.